Good morning. Today we're going to be taking a look at Boolean logic and how we can do some really cool things with it in computer science. Let's go ahead and take a look at the topics we have right here. So in Boolean logic, we've got a couple things we're going to look at. We have the basics. We're going to take a look at some truth tables, as well as how we can look at DeMorgans Law, or the more advanced form of Boolean logic, what we can do with that. So we'll go ahead and move past that. We have some symbols we have to make sure we're able to understand when we're talking about Boolean logic. We're going to abbreviate truth with I'm going to abbreviate true with T, false with F, just because it's quick and easy. My not is going to be a giant exclamation point or just a regular simple one. Ampersand, I suck at drawing ampersands. There is no good way for it. So mine's basically like a curvy plus sign thing, maybe a fish-ish, I'm not sure. As long as you're consistent with it on the AP exam as well, you're good to go. But this is what mine usually look like. My ORs are standard. Hey, 2 pipe keys in a row, we're good to go. So the symbols you have to know when we're talking about Boolean logic. All right, some of the basics. So the first thing on the basics we have to address is the idea of order operations. No, wait, I know this is not algebra, but it's Boolean algebra, so it still is the same basic thing. We have some rules we have to follow. The first and foremost, just like in regular math land, parentheses matter. They're important, they're a big deal. We do those first. Then we have the not symbol, not second after parens. Then we have and then we have or. And of course we have the and equals and or equals, but we're not going to worry about the combination equivalent here for that. But the left to right also applies, so it's just like regular math and logic, so we keep that going. Our not symbol is the great inverter. This is how we change the values of something. And so not inverts values automatically. So not a true expression becomes a false expression. Not a false expression becomes now a true expression. So we can change things from true to false and back and forth, vice versa. We also have the fact that the not operator inverts relational operations as well. So not x is less than 3 becomes x is greater than or equal to 3. It takes an exclusive operator, inverts it, and flips it to be an inclusive in the opposite direction. So not less than becomes greater than or equal to. Not greater or equal to becomes less than. So there's a direct inverse on that. So it takes it opposite direction. So it takes the alligator symbol, changes the other direction, and adds an equal sign to it if it's an exclusive. If it was inclusive, becomes exclusive again. You've probably already done truth tables in your computer science class. And a truth table, again, is how we evaluate the logical expression or the Boolean expression, figuring out what the values possible are. And so you have to define the combinations we have for the inputs and the resulting output from that expression. So if we have a Boolean test, x and y, semicolon, so we're going to assign into test whatever the result of x and y is. We have to make sure we give all the possible combinations of both true and false to both x and y, and the resulting operations for this. So if x is true and y is true, x and y results in a true value. If x is true, y is false, we have a false value. False and true is still false, and false, yes, that's right, it's false too. And so a truth table is just an expression of this. You have as many inputs as necessary, become a section over here. The resulting expression right here is those evaluations. You can always combine them into little pieces like that, break it apart, make it more simple, just like you're doing a regular math equation. So you can solve parts and then put it together to solve the bigger whole. And that's a great thing you can do in practice with that as well. Another amazing tool of logical expressions and logical evaluation is the power of short-circuit evaluation. This is the lazy evaluation. This is a great way to cut down the time and to look at things properly. You'll use this all the time when you're talking about user input, when you're talking about verification of sources, because you want to make sure that you don't have a null accidentally. So you check those things first. And so that's what we're talking about right here. So for short-circuit evaluation, also known as lazy evaluation, we have to make sure we do things properly. And the way we do that is by looking as little as possible. So the first false you get in an AND expression fails the test. As soon as you get a false, you're out. Same thing opposite though with a OR. The first time you get a true in an OR expression, you pass the test. You're automatically in. And so if you're using a logical structure like this, the fail fast works really well on an AND. So if you have a null, rather than getting a null pointer exception later down the line in your complex piece of code, you test for a null first, and you don't have to worry about having a null pointer exception later on. Same thing as soon as you want to get a true value. You don't want to test all the things you're working with. You only want to test the values you absolutely have to. And so as soon as you get a true, you pass that test and you go inside. And that's with an OR. An AND is only for the things that have to all be true, and OR is for the one where only one has to be true. We have this cute little mnemonic so you can help understand and organize your thoughts around this. Anytime you need all to be true, that's an AND, or when AND is there, it all has to be true, because an AND requires everything in the statement to value it to be a true, because it's the only way it works. On an OR, first letter OR means only one has to be true. So you've got that match right there. So O for one, O for OR, A for all, A for and. Great way to remember what you have to do with that. So that's just that little logic right there. Now, we want to do a quick introduction to the idea of DeMorgans laws. This is how you're going to simplify and or decompose a logical expression to its component pieces, because a lot of the time you have really complex problems. You have to figure out the little pieces and figure out how to make that happen. And so DeMorgans law is how that occurs. And so we distribute or simplify any logical expressions. So that's what DeMorgans law is all about. So let's see a couple examples of that. We have a really simple example of DeMorgans right here. We have not and the value of x or y. And so that becomes right here, we take an inversion on that, so the inverts across like this, because the inversion works across the entire thing. It distributes just like -1 multiplying on a regular algebraic equation. And so we have not x, inverting that. It inverts the operation as well. It goes from an or to an and then the not also operates on the y, so we have a y right here. So we have not x and not y. So a not x or y becomes not x and not y. So that's the way that structure works, and there's some more stuff you can do to look at that. Let's see a more advanced version. We have a more advanced version of DeMorgans law right here, where we have not x and not x and y. So we're going to distribute that apart, so we now have still that not x because there's nothing changing on that. The and stays the same right here. And then we have the not x becomes x. The not and becomes or, and the not multiplies on the y to become not y. So we now have a new simplification. We have their x and not x right here with this, so not x and x. Those are going to cancel each other out because that become simply just automatically false. And then we have an or, so false or, which means we don't have to even worry about this. We simply have not y is what that comes down into play. So we have the logical expression broken down from this complex sequence right here. We first distribute the not across to get this. We then cancel out the not x and x because that's always going to be false, because not true and false is going to be, so not true plus true is going to be false and true, which is automatically false. Not false and false is false, so it still doesn't matter. And we have our or, so we just automatically can evaluate that without even looking at it, and we only have not y for that solution. And so that's a great way we can look at how we can use DeMorgans law to break down and simplify some of our equations. And that's just a quick review of Boolean logic and DeMorgans law. Thanks. Have a good day. We'll see you next time.